Hello, my name is David Fansler, and this is Lesson 4 on using the GLG Community Toolkit. In this lesson, we'll take a look at the C code that drives the window drawing that we created last week. But before we do, we need to make a change to the window, because I forgot something that should be done with every program, and that is to provide an elegant way to exit the program. So let's go to home/pi GLG to bin and to GLG Builder X11 no OpenGL. So we'll execute that. And let's open our file. So we'll go to Open, discard that one. We want to backspace to Pi. Scroll down. Now I always put my programming projects in a separate directory, and it's called Projects. And within that directory, there are other directories that have the actual code for the different projects. So this is lesson 4. So we go down to lesson_3.g. All right, so here is our program, our drawing. Let's move this out of the way for a moment. We got to get down here to that down arrow. So now we can start making changes. So let's go to Palettes, to Push Buttons, choose as a push button, and move it down here. All right, we don't need that anymore. All right, this is highlighted, and it's called Widget. Well, we don't want it to be called Widget. We want it to be called Quit Button. And let's go to another screen here. We want to change the label string to be quit. And the label itself, to make changes to it, let's change the font size. All right, 6 is too big, 5 looks a little weird. Okay, so we'll use this one. We say okay to that. And we're done with that. So let's save it. It's okay to overwrite. And so now we have our quit button installed. It's that easy to put it in. Looking at our C code. Now, what I typically do is that I will go, let me show you, to Pi, to GLG, to the examples in C, to the dashboard, and GLG dashboard G.C. I will use that as the basis for the program that I'm going to create. And the reason for that is we know this thing already works. And it has all the different things that are kind of unique to a GLG program. So that's what I use. I just simply copy it. And in this case, it's lesson 4. So I've added a number of additional includes for various reasons. One in particular is that the analog to digital converter that we use is a I2C or IC squared device. And so we need to add those definitions in there. Now, I prefer to do this over using Wiring Pi or the library or the BCM 2835 library. I prefer to address it directly. All right, so scrolling down this, these voids right here are the prototype functions for the functions that are already included within this particular C program. Double intensity is the value that I assign to the ADC value when it comes back. We have our update interval of 100 milliseconds, a tenth of a second. Use tags is false. Scrolling down, the next thing we need to change is drawing. Load the drawing from the file. So this is what we created using Graphics Builder. So the name of that file was lesson_3.g, so we put that there. And then the screen name is what shows up at the top. Oh, I can't see it in this one, can we? All right, this is what the screen name is. This is what shows up at the top of the window. So we're going to change this to lesson 3 and 4 example. That's all we need to do in that particular issue. The initialized drawing. Now there were several things in this that initialized the drawing. You could, if you had dials, you could set the high and the low and things like that. We don't need any of that except for this run value equals 0. Run value is an integer, and I created this as a flag to tell me if the lamp button is on start or stop. And that controls whether or not the ADC runs. Update the drawing, use tags. I don't use tags like I said, I use resources. So I just commented all that out. Now I left them in there in case at some point in the future I decide to use tags, then this is here as an example of how the tags are used. But I did put a semicolon inside of the brackets. Else if run value equals 0. This is the integer we were just talking about, the flag for the condition of the start stop button. Debug 1 equals 1. Now this is something that I add into my programs. Over in the BSPH, there are two defines here. One is called debug and the other is called debug 1. Debug 1 has a lot more printf statements in it than debug does. So we don't need all those printf statements at this point, so we're just going to use the debug. So if debug 1 was true, then it would print this call the ADC to let us know that that was taking place. But it's not, so we don't use it. But what happens is if the run value is equal to 0, then we're going to run the ADC read. So that reads the channel, well, in this case, channel 0 from the ADC. There's 4 channels, 0, 1, 2, and 3. This particular function uses as an argument the channel number that you want to read. So once it comes back, the ADC value is put into intensity, and then we set that double value into the drawing into lamp intensity \value. Value is an attribute of the value display. So that's what's going to change the value in the value display. And of course we're using intensity as the argument for value. Now here is debug. So this is the one that has fewer debug statements in it, or printf statements. So it says if debug is equal to 1, which is true, then we're going to do a printf, and we're going to print out the raw value of the analog to digital converter, and we can compare that with the scaled value that we come up with later. All right, we update the drawing, and then we start the timer over again. These two things, start updates, stop updates, we don't need to make any changes to them at all. Input, this is where a whole lot of things happen in this program. And what we get from messages from the different widgets is either a format message, an action message, or an origin message. So here's our debug again, we'll ignore that. So here's what happens. First off, we're going to look to see if the window is equal to 0 and if the delete window has been activated. That's that little X up here in the corner. Now, what that does is that if it has been activated, then it will exit the GLG. If we don't have that in there, then the GLG is still out there in memory floating around, and it could cause us problems later. So then we come to let's see, that was that. If the format is button, then we take a look and it's equal to 0, then we take a look and we're going to printf is equal to button as part of the debug. So we need to find out which one it is. So if it's active, then we're going to go down here and say if the origin is the quit button, then we're going to exit the program. We also need to look to see if the value has changed on the lamp button or the on-off button. And so we look to see if there has been a value change. If there has, then we look to see if it's the lamp, and if it's equal to 0, we do a debug, and then we create a new value or we create a new variable, a double called value, and we get the double resource from the on state, and we put it into a pointer of value, and then we use that to determine what the value is of the start stop button. So we're just using a switch. So if case is equal to 0, then we're going to set the run value to 0. We're going to stop the updates, which will stop the analog to digital converter from running. We break. If it's case 1, then we set the run value to 1 and we start the updates and we break. After that, we're going to update the viewport within that, and then we're going to we have a debug we don't use. This set size, we don't use that. We don't need to worry about that, I should say. That is already provided, and it's just something we do within the program to set the size of the window. Get data is for creating simulated data, so we don't need to worry with that. Now, this last function is one that I created called delay, and it just takes a value called DT, and it counts down from 1,000 to 0, or it counts up to 1,000 from 0, and it'll do it the number of times that we put in this argument called dtime. Now, notice that we don't see the analog to digital converter program. And that's because instead of loading this thing up with all sorts of functions, I've created a separate program for the analog to digital converter. Now, it contains a lot of the same functions that the includes that were in the main program. Again, here it is, ADC read, and we're going to use the channel number as an argument. Now, for IC squared, this is a very powerful and a very useful interface that allows you to interface to a lot of different devices. One thing that I guess I ought to bring this up is that there is a program that if it's not installed on your computer already, you should do it. And it's called IC2, maybe I2C, we'll see, detect. And you put with it -y and 1. Okay, so it is I2C. All right, so let's back up. All right, what this shows us is the address of any IC squared device that is attached to our Raspberry Pi. Hex 48 is the address of the ADS1115 analog to digital converter. So we know it's out there. This is a very helpful thing in knowing that our devices are out there. Notice we don't have any other devices at this point. We will, next week we'll have another device or next lesson we'll have another device installed. So what we do is that we open this as a kind of like a file pointer. We open the dev I2C-1, and if it's less than 0, then we've got an error. But if it's 0 or greater, then we run the IOCTL, and we tell it the address of the device that we want to use, the ADC address. And that's located in BSP, which BSP, by the way, it stands for Board Support Package. And here's the ADC underscore address value of OX48, which is what we saw when we looked at the I2C detect 48. Back here, what that gives us is this FDC is kind of a file pointer. And again, we're going to use that to talk to the analog to digital converter. Now, when you use this particular analog to digital converter, there's 3 items or commands that you have to feed to it. And these are done through an array. And the first, the 0 value of the array is always set to 1. That's the configuration register we're using. The third value is always set to OB1 and then 7 zeros. The one that's in the middle, the AD buff 1, is the channel that we want to convert. So we use another switch with the channel number, and if the case is 0, then we set AD underscore buff 1 to OB11000011. Now it's these last 4 digits that change according to what channel we are doing. So it starts off as 1100. If it's case 1, it's 1101. If it's case 2, it's 1110. And if it's case 3, it's 1111. So once we've done that, we write the array to the analog to digital converter. And this is telling it that there are 3 variables that we're going to assign to it. And if we don't get 3 back, then we did something wrong. Here we write to it that we want to read the buffer. And we read the buffer, and it's 2 8-bit values. So that's why it's read buff and then a 2. We're reading 2 8-bit values that we have to put together to make a 16-bit value, which is the output of the analog to digital converter. Now, the way that I do this is that I take read buff 0 and multiply it by 256. That moves it. That's basically the same thing as moving it 8 places to the left. And then I add to it read buff 1, which is the lower byte of the 16 bits of the analog to digital converter. Now sometimes when the values are real low, an ADC may give you something less than 0. So the program doesn't like that a whole lot. So what we do right here is we say if the value that we got from the ADC is less than 0, then we're going to set it to 0. The last thing we do with that value is that we scale it. So it's a float. Well, yeah. The last thing we do with this value is that we're going to scale it. So we take value and divide it by 100, and then we divide that by 2.5, and that will give us a range of 0 to 100. We close the I2C and we have a little delay, and then we return. So that's this program. So let's go back here, and I'm going to put in a space. And the reason I'm doing that is that occasionally, if you don't make a change to the program and you run makefile, it'll come back and say, well, there's nothing to do. You hadn't changed the program. Speaking of makefile, let's go over and take a look at it. So it's set for C, and we come down, and these things are just like they were last lesson, except for one thing that we need to add to it. Here the target is lesson 4, but we need to add a file. We need to add the ADC file. And the way we do that is that we type in under additional files, adc.o. Now, by doing that, what happens is that the program knows, the makefile knows, that if we have an adc.o, then there has to be an adc.c, and it will go out and create that program, or run that program. It will compile that program. What happens here is that the makefile sees there is an adc.o, then it knows there's an adc.c, and it will go out and get that file and compile it to become the adc.o. All right, so that's everything that we need. So let's save everything. By the way, this is the Geany editor that comes with the Raspberry Pi. I find it to be very good, very convenient. So let's bring our window back in, our terminal window. All right, we're going to make our file now. So the way that we do that is that we type make -f makefile. All right, that ran cleanly. So all we do now is we run the program. So sudo, and the reason it has to be sudo is that access to the peripherals on the Raspberry Pi are guarded by the operating system. So we have to be the super user in order to be able to reach those peripherals like the I2C. Period / lesson 4. We need to turn off the OpenGL, so -glg -disable -OpenGL. Before we actually bring our drawing window in, let's take a look at what's being produced here. This is what the printfs are doing. They're giving us the raw value from the analog to digital converter, and they're giving us the scaled value. So if I move the joystick down, notice that it goes to a value of 36, which gives us a read value of 0.1. And if I go up with the joystick, it climbs to roughly 24,000 and a value of 95.6. That will change some. There we go. I did it again, and it gives us 25,000, and 100.7 is the scaled value. So taking a look at our window, as I move the joystick up and down, we see the lamp intensity changes. If I turn this off, I'm moving the joystick and nothing's happening. Right, I'm going to leave the joystick where it is at 0, turn it back on, and immediately it goes to 0. So we can see that works as it should. So we've got a tie-in between the on-off button and the lamp intensity, or the analog to digital converter. The quit button, we put it in a minute ago, and if we click on it, then we're done. So that gives you an example of how these things work. We have successfully created a window that has a drawing in it from the GLG Community Toolkit using Graphics Builder. And then we created a C program that access the buttons that are on the drawing, and then it also outputs the analog to digital converter to be displayed on the value display. Now, in the next lesson, lesson 5, we're going to look at how we can actually create a pulse width modulated signal that will follow the lamp intensity, and if we hook up an LED to it, it will change the intensity of the LED. So that gives us not only a hardware input with the analog to digital converter, but it gives us a output to the real world in the form of a pulse width modulator. I hope you enjoyed this lesson. Leave a like, subscribe, send me a message. This is David Fansler until the next lesson, saying happy programming.